Section: Introduction. In this section, we explore in-context learning, ICL, a fascinating ability of large language models, LLMs, to learn and generalize from new information presented in their input, even if they haven't encountered similar data during training. We were among the first to showcase this capability in LLMs, and since then, many studies have sought to understand how ICL arises. It's important to note that ICL isn't confined to natural language processing. Various synthetic scenarios have been created to investigate this phenomenon further. Recent research has examined ICL through the lens of data distribution properties. Specifically, we recognize the significance of common and rare classes in driving both in-context learning and in-weight learning, IWL. We found that ICL can occur in transformer models when there is considerable variation within classes and a large number of classes. Additionally, we observed that both ICL and IWL can happen together when class distributions follow a Zipfian pattern, although ICL may become less stable in extensive training scenarios. Our work is inspired by this distributional perspective, and we delve deeper into how data distribution affects a transformer's ability to learn and apply in-weight and in-context predictors across different input areas. We provide insights into ICL in synthetic settings through theoretical analysis and experiments, and we connect these findings to practical applications by demonstrating similar behaviors in a straightforward NLP task using a real LLM, Gemini Nano 1. We present a simple theoretical model showing that ICL can both emerge and become transient in scenarios with infinite data. Our model highlights that two types of data are essential: one where similar observations frequently appear, promoting in-weight learning, and another with diverse, rare data points that encourage in-context learning. Through our analysis, we identify conditions under which both learning types arise. Specifically, the presence of in-weight data fosters in-weight learning, while in-context data leads to in-context learning. This aligns with previous empirical findings, indicating that when enough in-context samples are available, ICL emerges, particularly with rare class samples. As we train models on more samples, the in-context data can transition into in-weight data, which may reduce the model's reliance on in-context learning. We empirically validate that training transformers on synthetic and omniglot data aligns with our theoretical predictions. Furthermore, we demonstrate that fine-tuning a large language model to memorize specific data can diminish its in-context learning capabilities. While we do not focus on how transformers learn circuits for ICL, we acknowledge that this ability can arise from extensive in-context training data and a sufficiently expressive architecture. Several studies have explored the mechanisms behind ICL, showing that transformers can learn simple tasks and implement various algorithms in context. Our investigation differs as we examine how ICL can emerge from context sequences related to a single task, rather than multiple tasks. Section Summary. In this section, we explore in-context learning, ICL, in large language models, LLMs, demonstrating how the distributional properties of data influence the emergence of ICL and in-weight learning, IWL. Our theoretical model reveals that the presence of both common and rare classes in training data can lead to these learning phenomena, and we empirically validate our findings using synthetic data and a real LLM, showing that fine-tuning can reduce ICL capabilities. Section: Theoretical Analysis. In this section, we present our theoretical model. We consider a bi-level model that learns two types of predictors, one that memorizes weights, which we call G, and another that uses context, which we call H. For each input, we choose the predictor that is expected to perform better for that specific data point. The predictor G can be learned accurately in areas where we have sufficient training data, while H can be effective wherever the context is relevant. Ultimately, the model's performance will depend on the expected accuracy of both G and H for a given input. We will formalize this approach in the context of tabular classification problems. In our setting, we define a finite input space X and let C represent the number of classes. The labels are represented in a C-dimensional simplex. We have a training dataset S consisting of n examples, where each example includes a context made up of L additional input label pairs. Each training example is denoted as a combination of these pairs along with the main input and its label. We assume that these examples are drawn from a true distribution D, and our task during training is to predict the label given the context. Our ultimate goal is to minimize the prediction error for new samples drawn independently from D. We measure prediction error using a loss function that takes two labels and outputs a value between 0 and 1. We can scale the loss, so we assume it is bounded by 1 and is convex in its first argument, which is true for common loss functions like cross-entropy and squared loss. Next, we consider a scenario where inputs may have label noise. There exists a mapping that defines the true label for each input. When we sample an input, we also sample its label based on this mapping. We then formalize two classes of learning, the in-weight learning, IWL, class, which uses only the query, and the in-context learning, ICL, class, which relies on labels from the context. The IWL class consists of functions that learn a separate mapping from each input to the label space. The ICL class uses the labels in the context to make predictions and is designed to output a combination of these labels. We also incorporate a uniform distribution to ensure numerical stability in our predictions. Section Summary. In this section, we present a bi-level theoretical model that incorporates both an in-weight predictor, G, and an in-context predictor, H, to optimize predictions based on the expected accuracy for given inputs. We formalize this approach within tabular classification problems, considering a training dataset with context and addressing label noise in the data generating process. Section: Simple Model. In this section, we design a model that chooses between in-weight and in-context learners using a function, which we call alpha. This function can take different values between 0 and 1 for each input. We analyze a simplified model to understand how in-context and in-weight learning develop. For each input, our model combines the outputs of the in-weight learner and the in-context learner based on the value of alpha. We observe that in-context learning tends to appear when the data has many rare classes. We explore the idea that in-context learning arises because in-weight learning struggles with classes that have few training samples. First, we measure the generalization error of the in-weight learner. Then, we look at a specific type of in-context learners and establish upper and lower limits on their prediction errors. We start by stating a common generalization bound for a learning algorithm. If we have a set of examples drawn from a data distribution, we can define subsets based on specific queries. We denote the number of examples in a subset as n_x. The empirical risk minimizer is the function that minimizes the average loss over the examples in that subset. We also define an upper limit on the gradients of the loss function. With a certain level of confidence, we can say that the risk of our empirical risk minimizer is bounded by a combination of the optimal risk and a term that decreases with more examples. Inspired by mechanisms in transformers, we consider a function class for in-context learning that averages predictions based on the similarity of context vectors to the query. If the context includes irrelevant labels, the prediction can become noisy. We analyze how the number of irrelevant labels affects the prediction error. When we specialize our loss function to cross-entropy loss, we find that if the input does not contain a relevant label, the loss is high. If there are irrelevant labels, the loss can be expressed in terms of the number of irrelevant labels and other parameters. Our findings indicate that the test error of the in-weight predictor improves at a certain rate, while the in-context predictor's error depends on the number of irrelevant labels. In cases where the true labels have low variance, the in-weight predictor can outperform the in-context predictor given enough samples. We illustrate these bounds in a figure. Initially, the in-context predictor may perform better with few samples, but the in-weight predictor eventually achieves lower error with more examples. We propose an oracle algorithm that selects between the in-weight and in-context predictors based on their expected test errors. This algorithm predicts outcomes by weighing the two predictors according to their performance. We find that in-context learning first appears in rare classes but is eventually outperformed by the in-weight predictor as more data is processed. This aligns with our observations that in-context learning is more prevalent with rare classes in the training data and diminishes as training continues. Section Summary. In this section, we propose a model that dynamically selects between in-weight and in-context learners based on a function that varies for each input, analyzing how in-context learning, ICL, emerges particularly for rare classes due to the higher error rates of in-weight learning. We establish that while ICL may initially perform better with limited samples, the in-weight predictor ultimately converges to lower error rates as more data becomes available, aligning with empirical observations of ICL's behavior in training scenarios. Section: Learning to use in-context versus in-weight learning. In this section, we explore the differences between in-context and in-weight learning. We note that during training, our model does not see the test error. We aim to connect the ideal algorithm with the behavior of a simpler model trained using gradient methods. We follow a standard training approach. For each sample, we predict a function based on a combination of two models, weighted by a parameter. We update our parameters based on the loss we observe from our predictions. Typically, we use a gradient-based method to update these parameters. Under certain conditions, these methods can converge to a local optimum and ensure that the regret, which measures how much worse our model performs compared to the best possible model, grows slowly as we train. Sublinear regret indicates that our average loss will approach that of the best predictor. We emphasize that when minimizing regret, the parameters we use for predictions at each step are based on previously observed data and are evaluated on new data. This aligns with our earlier recommendation to choose between in-weight and in-context predictors based on their performance on unseen data. For simplicity, we consider a two-level parameter update process. Since one of our models is tabular, it can provide the best fixed predictor for each input. We show that the regret of our algorithm is limited by the regret of learning the parameters. If the algorithms we use for learning these parameters have no regret, then our overall algorithm will also have sublinear regret. We also note that under linear losses, the best choice of parameters will minimize total loss for each input. We define the optimal parameter choice based on the observed losses. Our algorithm satisfies certain conditions that ensure sublinear regret, which is achievable with common gradient methods. If our training examples are drawn independently from a population, we can expect the average loss of our model to behave similarly to generalization error guarantees. We show that even though our model does not see test error directly during training, the losses from training samples can act like test losses, providing useful feedback. As long as our learning algorithms are no regret, the final predictor we develop will closely match the performance of the optimal predictor. This means that our learned model will effectively choose between in-context and in-weight predictions based on their performance. We conclude that the unrealistic notion of selecting predictors based on unknown test error can be replaced by a decision-making process learned during training, similar to gradient descent. We will demonstrate through experiments in the next section that our simple models yield valid predictions in many practical situations. Section Summary. In this section, we bridge the gap between oracle algorithms and simple models by demonstrating that our training procedure, which updates parameters based on observed losses, leads to sublinear regret when using no-regret algorithms. This implies that our learned model can effectively choose between in-context and in-weight predictors based on their performance during training, rather than relying on unknown test errors. Section: Experiments. In this section, we demonstrate through various experiments that our straightforward theoretical model is effective in predicting and explaining the relationship between in-context learning, ICL, and in-distribution learning, IWL, in real-world scenarios. For our synthetic classification task, we explore how the errors from ICL and IWL predictors can indicate whether a transformer trained end-to-end will show ICL capabilities. We also examine how different parameters influence the emergence and duration of ICL, which we detail in the appendix. We focus on a classification problem with an imbalanced data distribution, featuring both high-frequency and low-frequency classes. We denote the high-frequency class labels as C_H and the low-frequency class labels as C_L. Combining them into a set C, each sample starts with selecting a target query response pair, X, Y, and then generating the context sequence. The input-output pair, X, Y, is drawn from a joint distribution, which we call the base distribution. We first sample a label from a mixture of uniform distributions over C_H and C_L, weighted by probabilities for high and low frequencies. We assume that the probability for high-frequency classes is much greater than that for low-frequency classes. The distribution of queries for each class is defined by a prototype vector from a unit sphere. For each class, we sample this vector uniformly, and then we create X by normalizing a perturbed version of the prototype vector, where the perturbation follows a Gaussian distribution. To generate the context for a query target pair, X, Y, we first decide if the context should be relevant, meaning it must include at least one pair from the same class. We then sample L input-output pairs independently, ensuring that a class Y sample is included only if the context is deemed relevant. In our experimental setup, we train a transformer model end-to-end. Our models consist of two transformer decoder layers, each with a single attention head, processing 64-dimensional embeddings. We use linear projections for both input and output tokenizers. For predictions, we take the last token output from the final transformer block and pass it through a linear layer followed by a softmax function. To assess the challenges of IWL and ICL, we train two separate transformers using data with different relevance probabilities. We label these models as IW and IC predictors. A generic model trained on data with a high probability for high-frequency classes is simply referred to as the transformer. All models are trained using cross-entropy loss for 50,000 gradient updates with a batch size of 32. We set the high-frequency class labels as 0, 1, 2, 3, 4, and the low-frequency class labels as 5, 6, 7, 8, 9, with an input dimension of 64. We also fix the context length at 1 and vary the total number of samples across a range of values. Each experiment is repeated 5 times, and we present confidence intervals based on one standard deviation in our figures. For evaluation, we assess whether the trained models demonstrate IWL or ICL by testing them on both in-base distribution, IBD, and out-of-base distribution, OOBD, data. The OOBD is created by cyclically shifting the labels of the classes. A purely IW predictor trained on the base distribution will struggle with OOBD data, while it can predict ICL if the context is relevant. A model that only exhibits IWL will show low error on IBD regardless of context relevance but will perform poorly on OOBD. Conversely, a model that only demonstrates ICL will have low error on relevant contexts but high error on irrelevant ones. Section Summary. In this section, we demonstrate that our theoretical model effectively predicts the relationship between in-context learning, ICL, and in-distribution learning, IWL, through various experiments, including a synthetic classification task with imbalanced data. We evaluate transformer models trained under different conditions to assess their performance on in-base and out-of-base distributions, revealing distinct behaviors indicative of IWL and ICL capabilities. Section: Main Results. In this section, we aim to identify the conditions under which in-context learning, ICL, appears and whether it is temporary. Our experiments show that even slight changes in input can trigger ICL capabilities in the transformer. As we increase the dataset size, the in-context, IC predictor shows higher error rates compared to the in-weight, IW predictor, indicating that the transformer is losing its ICL abilities. We also notice that ICL fades more quickly for high-frequency classes than for low-frequency ones, as the IW predictor needs more samples to reduce error significantly. This leads to a phase where the transformer can perform both ICL and in-weight learning, IWL, at the same time. We find that adjusting input noise influences the emergence and persistence of ICL during training. Our theory suggests that more noise complicates the learning process for the IW predictor, making ICL more likely to appear and last longer with higher noise levels. For instance, we observe that ICL rarely appears with no noise, while it remains consistent with a moderate noise level. Additionally, we visualize the error rates of IC and IW predictors and see that the IW predictor performs worse under higher noise, confirming our theory that the transformer alternates between ICL and IWL based on error rates. Next, we explore how varying distributional parameters affects ICL performance. Our findings indicate that ICL is stronger with fewer high-frequency samples and more relevant samples. Fewer high-frequency samples increase the number of low-frequency class samples, which helps the IW predictor reduce error. More relevant samples reduce bias in the IC predictor, promoting ICL. However, increasing the number of low-frequency classes makes it harder for ICL to develop, although it diminishes more slowly due to the complexity of learning mappings for more classes. We also find that longer context lengths hinder ICL emergence because they introduce more distractions, making it harder to identify relevant examples. To test this, we fix the context length and vary the number of relevant contexts. We see that with only one relevant context, the error rates for IC and IW predictors are similar. As we increase the number of relevant contexts, the IC predictor initially performs better, indicating that fewer relevant contexts are indeed more challenging to learn from. Finally, we apply our findings to a natural few-shot learning dataset, Omniglot, which contains images of handwritten characters. We use a ResNet to convert images into a 64-dimensional embedding. Our data setup includes a context length of 8, with 3 relevant and 3 irrelevant examples. We also model the base level distribution to be Zipfian. We set the context length to 2 with varying relevant contexts and a small amount of input noise. We categorize the first 20 classes as high frequency and the remaining as low frequency, varying the number of samples and training all models for a set number of gradient steps, repeating each experiment multiple times for reliability. Section Summary. In this section, we explore the conditions under which in-context learning, ICL, emerges and persists in transformers, finding that slight input perturbations and varying noise levels significantly influence ICL capabilities. Our experiments reveal that ICL is stronger with specific distributional parameters and diminishes more slowly for low-frequency classes, while also demonstrating that longer context lengths hinder ICL emergence due to increased distractor contexts. Section: Results. In this section, we observe trends similar to those in the previous section, but with some important differences. First, we note that even when we increase the image noise, in-context learning, ICL, does not occur for high-frequency classes, while it consistently happens for low-frequency classes. This aligns with our theory, as the in-batch distribution, IBD, error for the chosen IC learner is much lower for low-frequency classes. Additionally, both the IC and in-weight, IW, predictors show comparable IBD errors for high-frequency classes, indicating that IWL is more likely to occur for common classes, even with increased input noise. We delve deeper into this in the appendix. For the Omniglot dataset, we find that ICL can easily emerge for low-frequency classes. Even when we increase the context length and the relevant context is low, the transformer still manages to perform ICL. However, we notice that ICL remains temporary and of low quality as we increase the number of samples. Next, we conclude our experiments by examining the impact of IWL on the ICL capabilities of a real language model, specifically Gemini Nano 1, which has 1.8 billion parameters. To encourage memorization, we fine-tuned the model to remember where certain individuals live. The fine-tuning dataset includes 8 questions about people's residences, featuring 4 real and 4 fictional names and cities. This setup requires the model to depend on IWL to learn the connections between names and cities. Our results show that the fine-tuned model accurately predicts the real name and city pairs in the dataset, while it struggles with the fictional pairs, getting them wrong about half the time. In contrast, the base model fails to answer any questions correctly. To assess ICL capability, we introduce a scenario where we state that a person lives in a different city before asking the fine-tuning prompt. For instance, if we say that a person lives in the fictional city Kageyard, the base model consistently uses ICL and answers with Kageyard. However, the fine-tuned model sometimes defaults to IWL, suggesting that the in-wait information can override the in-context prediction from the base model. This demonstrates that ICL can be temporary even in real language models. We provide further discussion and observations in the appendix.